Okay, so thanks a lot for coming. Today it's a pleasure to have Tanio Diaz Santos visiting. Tanio had his PhD in Madrid in 2009, then did a postdoc for a couple of years in Crete, then moved to Caltech for 3 years, and then became a Conicet fellow in Santiago de Chile, in the Universidad Diego Portales, where he stayed for 7 years, 6 years, until 2020, when he returned to Europe, and he's now a senior researcher at the Institute for Astrophysics in Iraq and in Crete. Tanio is a fantastic scientist, one of the people I know with the deepest understanding of the inner working of the interstellar medium, and has been particularly productive in digging into the deepest parts of the galaxies to understand their secrets, and today will tell us some of them.
Thank you very much for this super nice introduction. I hope I'm at the level that you have put me. First of all, thank you very much for the invitation to give this colloquium. I hope you enjoy the talk. And today I'm gonna speak about the interstellar medium of the most luminous dusty galaxies near and far. This is a topic that covers a little bit what we know about the properties of these dusty galaxies, not only in the local universe, but I will also talk about a little bit about the most luminous objects, quasars in the high-redshift universe. And I would like to start by motivating or making a little bit of historical remarks on how these luminous infrared galaxies were discovered. They were discovered originally by a few of them in the 70s, but it was not until the late mid-80s when the IRAS space telescope was launched and discovered these luminous infrared galaxies in the hundreds, performing an all-sky survey in the infrared at 12, 25, 60, and 100 microns. And these galaxies are characterized by having infrared luminosities of larger than 10 to the 11, should be actually 11 to 12. And they were one of the most interesting facts about them is that apart from the obvious infrared luminosity output, right, that it comes from dust reprocessing the UV light from stars and AGN, was that the space density of these luminous infrared galaxies was very similar to the space density of optical quasars known at the time. So this prompted indirect link between these luminous infrared galaxies and the formation of quasars. And actually, it was a few decades or a decade later when this basically picture was put together, in which in this work by Hopkins and collaborators, they basically linked how galaxies could become quasars via the major merger events through spirals, gas-rich spirals. Right, so you have this phase in which the two galaxies start interacting, and they reach the coalescence, in which all or most of the gas lose their angular momentum and then fall into the nucleus of each of the galaxies, and then to the center of mass of the coalesced system. And basically, this triggers a lot of star formation and black hole accretion that peaks at the coalescent times. And this pileup of gas and dust into the center of these galaxies makes them optically thick, and we can observe them only in the infrared. where they are selected. And basically the feedback from these power sources, both from star formation and at the highest luminosities from quasars, then blows out the material around them, and then you have an elliptical galaxy at the end, right? So this is the paradigm that we have nowadays for the formation of quasars in the local universe. And I would like to also motivate a little bit luminous infrared galaxies from a more generic point of view, not only from the local universe, but also because of their nature. The infrared galaxies and quasars are perfect laboratories to study the triggering of thus obscure starbursts, and to understand the coevolution of star formation and supermassive black hole accretion across cosmic time, not only in the local universe. And here is a representation of why obscured galaxies are important in the grand scheme of things in galaxy evolution. And it's because between redshift 0 and redshift up to 3, they dominate the star formation rate density in the universe by an order of magnitude with respect to unobscured galaxies, right? And within this infrared population, we can dissect it in different luminosity beams, and we can see that at the low redshift, sub-lurks, still infrared, but galaxies with lower than 10 to the 11 solar luminosities, they dominate the population up to redshift 0.5, then lurks take over from 0.5 and up to redshift 2, and U-lurks represent a subdominant population that it's contributes significantly around redshift 2. So one thing that I don't think it's appreciated enough among the community is that once when people think about lurks and U-lurks, they think, okay, they are all really way above the main sequence of star-forming galaxies, right? But this is not completely correct, right? Because they also include normal sources, and not all of them are interacting, right? So they actually span the range between normal star-forming galaxies, and yes, the most extreme population of galaxies that contains the most powerful starbursts and quasars, at least in the local universe, right? So the majority of infrared galaxies are found in the interacting systems, but they cannot be also isolated. And they sample the full regime between main sequence galaxies and the most powerful starbursts. So they are not all really above. So despite of the significant advances that have been made since the 80s, since these luminous infrared galaxies were discovered, there are still many outstanding questions that we don't know about them. There are many. Do the nuclei of infrared galaxies dominate the production of energy, or are massive star-forming regions spread out over their disk also important? Right? All these tracers that allow us to age date the star cluster and evolution. Can we age date these star-forming regions that we find around the disks? Are these clusters destroyed in harsh environments? Have we discovered all the AGNs that we know inside of these luminous infrared galaxies? Can powerful starbursts change the state of the surrounding gas and the cooling channels? There are many questions that are still not yet answered. And from now on, I have split in a way this talk between the most recent results that we have been seeing from the JWST point of view for galaxies in the nearby universe, and then I will focus the second part of the talk on the population of dusty infrared quasars, also from results from JWST and ALMA. So the promise of JWST, as you probably are all familiar with this satellite, brand new satellite, this JWST provides a huge leap in sensitivity, 50 times more, times 10 spatial resolution and 5 times higher spectral solving power than compared with the Spitzer, right? And it's transforming the studies of the multi-phase ISM that we can map in this starburst and AGN. And these questions that I mentioned before, outstanding questions, can be tackled in terms of all the observables that can be probed with JWST in the mid-infrared regime. This goes from ionized atomic gas, with which we can track the ionization structure, the density and the properties of star-forming clumps. We can see warm molecular gas, with which we can assess the temperature, mass, and dynamics and feedback of warm molecular gas. And also we can take a look at the dust, including pHs and continuum, and determine the size, ionization state, and grains in photodissociation regions. This we can do it in terms of photometry, because JWST covers with a broad range of filters, medium and broad depth filters that go from 1 micron to up to 20-something micron, right? Or we can do it with near infrared and mid infrared integral field units like near spec IFU and MRS in MIDI that provide a coverage from 1 to 28 micron wavelength range at a resolving power of around 3000. And so these are a summary of the outstanding questions that I mentioned before. How do stars form and black hole growth emerging galaxies? How do they impact the ambient ISM on local star cluster scales? And what are the implications for the models of full and feedback, right? And these outstanding questions can be mapped into a discrete number of science topics that basically cover how the properties of nuclear star formation and stellar clusters. So we can measure their formation rates, their sizes, their ages. We can see whether merger triggered, if mergers trigger the formation of clusters, or on the other way around, they provoke their destruction. We can also identify AGN and characterize the nuclear power sources of many of these galaxies, because we have access to higher spatial resolutions, right? So we can isolate the power sources from the surrounding medium. And we can also take a look at the feedback from this nuclei. So I'm gonna talk about the latest results in this context using one of the largest samples of luminous infrared galaxies in the local universe. This is the gold sample, the Great Observatories All-Sky Large Survey, which is a sample of around 200 luminous infrared galaxies that have multi-wavelength coverage with basically the largest facilities that are currently and were online before. As I mentioned before, luminous infrared galaxies, they cover the entire merger sequence of galaxies and also bridge the gap between main sequence galaxies and starbursts. And the goal of this collaboration is to study the physics of star formation, black hole growth, and feedback in nearby infrared galaxies. We have obtained basically NIRCam and MIRI images, as well as NIRSpec and MIRI IFU spectroscopy for a bunch of them. This was part of an ERS program, these 4 galaxies. The NGC 7469, a safer one, a galaxy with containing a safer one nucleus, 3256, the starburst system, 2Zwicky-96, and BB114. So within this nearby universe, I have subdivided the results in this, as I mentioned, these 3 science topics. it's unsynchronized now. No, yes. Star formation and stellar clusters, identification of AGN, and feedback, right? So I'm going to start with star clusters. And because we know from previous observations from HST that suggests that the mergers can drive high rates of cluster destruction, right? In a constant star formation rate history, we expect, without the merger having any effect on the cluster population, we expect that the number of clusters per decade of age would be constant. But what we see is that there is a downturn in the number of clusters as a function of age, right? Where around 90% of the clusters are lost for every decade of magnitude increase in age. This effect of mergers are not only evident in the number of clusters that we see, but also in the average mass that we see for these clusters, right? Where we see a larger number of clusters per mass as we go into systems that are merging, basically. So mergers also appear to drive clusters to higher masses relative to normal galaxies. The problem here is that with HST, we couldn't access the ages, the star cluster ages in which you have the youngest populations. You have the young massive clusters. We see that there is a observed cluster destruction, but below 10 mega years, HST couldn't detect very young obscured clusters. But with HST, with JWST, sorry, we can now do that. And in a series of papers from Sean Linden and collaborators, for example, for this galaxy, BB114, they detected hundreds of compact star cluster candidates using near-infrared colors. In this case, 1.5 micron to 2 micron as a function of 2 micron to 3.5 micron, where you can see like the cloud of clusters here, but there is a subpopulation that can only be explained with very, very young ages and high extinctions of AVs larger than 5, right? So this 20% of these clusters are not observed at optical wavelengths. And this is a hidden population that of very extinguished young and massive star clusters that could not be detected with HST. A similar study by Bond and collaborators in which they use slightly different filters for the color diagnostics, but the result is the same. In this case, for the galaxy in NGC 7469, in the ring of star formation, there are many clusters that can only be reproduced with very, very young ages and strong extinctions, even with some contribution from hot dust. This increases the total percentage of young massive clusters from 15 to 48 in this particular galaxy. What about the power sources in luminous infrared galaxies? Well, for example, in 2096, this is a very interesting system in which there is a major merger going on in an advanced stage of interaction. These are two galaxies here that you see in the optical, but as you move into the near infrared and mid infrared regime, you see that they basically disappear, and all you see, for example, with MIPS, with Spitzer MIPS at 24 micron, was a point source, right? So now with JWST, we are able to resolve that point source, and we have discovered that this is we call D1, and this single compact source is responsible for 3 to 5 times to the 11 solar luminosities of this source, of this entire system, right? So 70% of the total infrared luminosity is produced by this little thing in here, which is unresolved. So, and it's dominant in the mid-infrared, but in the near-infrared, you couldn't guess that this is the most powerful energy source in the system. So here, for example, for another source, for BB114, we took a spectra of the two nuclear cores that exist in this galaxy, here. And we saw that for the first time that in one of the cores, because we couldn't access the 3 micron range from the ground, we saw that basically the spectrum of the southwest core was very, almost not featureless, but the 3.3 micron pH, which in some cases, the absence of it is related to pH destruction by a strong ionization field from a quasar or an AGN. It was very weak. So this prompted us to hypothesize that this core over here contains an AGN which was previously unidentified. In the other core, in the northeast core, there is a strong silicate absorption that we believe is still powered by embedded star formation. And the feedback, the last of the topics, we took a deep look and focus on NGC 7469, which is the galaxy that contains this safer one nucleus. And when we look at the point source at the central 100 parsec from this galaxy, we see very asymmetric and blue shifted profiles seen in the high ionization coronal lines, but not in low ionization atomic and molecular hydrogen lines. You can see a few examples of the shape of the lines, like neon 5, neon 6, sulfur 3, I think, and silicon 4, for example, where you see like this blue shifted emission that extends down to 1,700 kilometers per second, right? And you don't see that in low ionization lines, like in neon 2 or neon 3, for example. And one of the most interesting results from this work is that there was a correlation between the width of the high ionization lines and with their ionization potential, which basically is indirect evidence that we are looking at a decelerating stratified AGN-driven output. And we did some calculations, and we established that probably the mass outflow rate is around a few solar masses per year. And based on some scaling relations with the oxygen 4 line, we established that the black hole accretion rate should be of a few hundredths of solar masses per year. If we go a little bit zoom out from this nucleus and look at other highly ionized lines, for example, we can see that the magnesium 5 line, the contours is slightly extended towards the east, which is in agreement with a blue shifted outflowing wind that has been especially resolved, that is hitting the surrounding medium at a couple of hundred parsecs from the AGN. We also detect a very highly disturbed molecular gas, curiously in a direction that does not coincide with the emission of the high ionization lines. And we attribute that to turbulent motions created by shocks, perhaps also driven by the AGN. So this is a very complex source where we have, all kinds of phenomena that does not necessarily agree with the classical view of a bipolar outflow in which you have a highly ionized gas and everything is maps together in terms of geometry, but it's a complex system basically from which we have to learn many things here. And finally, for the analysis of feedback of the AGN, we were wondering whether the AGN would also have an impact on the properties of the interstellar medium on the ring of a star formation. So in this work from Lion collaborators, they put several apertures around this ring and look at the spectra and the mid-infrared spectra with MIRI. And they took a look in particular to polycyclic aromatic hydrocarbons. That if you were there yesterday in the lunch talk, I talked a little bit about them. I don't have time to explain all the physics inside them now, but this is a diagnostic diagram in which you can see or you can estimate what is the level of ionization and number of the size of these molecules. And basically what Thomas Lai found is that pHs appear to have larger sizes in the inner region of the ring, but not the pH ratios seem to be normal in the rest of the ring. So if the AGN has any effect on the ionization of pHs, it's only in the surface of the ring that is exposed to the radiation, potential radiation from the AGN. And also, he found that the pH intensities are correlated with the hardness of the radiation field, suggestive of dust processing from photodissociation and photodissociation. But the AGN feedback is limited to the inner region of the ring. So it's not that radiation from the AGN is destroying pHs at larger distances. In fact, as long as you have a little bit of a star formation, you will have pH emission, no problem. So these are the conclusions from, well, and I'm, I think, how much time? 20 minutes. 20 minutes, okay, very good. So these are the conclusions from the local universe. We find new populations of very young, very massive, young massive clusters that were previously unidentified with HST, likely due to their extreme obscuration, and they seem to account for a significant fraction of the total cluster population, right? JWST is able to spatially resolve for the first time the mid-infrared sources powering these nearby luminous infrared galaxies, in some cases revealing compact sources with extreme luminosities, for example, previously unidentified AGN in BB114. And finally, AGN feedback can be identified in nuclear regions, unresolved down to less than 200 parsec via high ionization coronal lines, which show very broad blue shifted components. And we also find shocked and turbulent molecular gas in these certain nuclear regions. So now I'm going to move to the far universe, and I'm going to focus on basically an aspect that I introduced in the beginning, which is the paradigm that we have on the formation of quasars. So in order to motivate a little bit more why quasars are important, is probably you have seen this 1,000 times, is that, well, we measure a distribution on the number of galaxies per stellar mass that does not agree with lambda CDM. Basically, we see less galaxies at low masses and at high masses compared with what we should be expecting. And this means that there must be a mechanism or multiple mechanisms that prevent galaxies from forming stars, both at the low mass end and the high mass end. At the low mass end, we believe that it's basically turbulence-driven star formation feedback that has an important effect on small galaxies because they have low gravitational potentials, so they can drive out gas and quench star formation relatively easy if you have a burst of a star formation. But at the high mass end distribution of galaxies, you need some more powerful energetic phenomena because there the gravitational potentials are stronger, right? So the most likely mechanism at higher mass is this momentum-driven quasar AGN or A/AGN feedback, right? And as we saw before, the paradigm in the local universe to form a quasar is this major merger of two gas-rich galaxies. However, at high redshift, we know that the conditions in galaxies are different from the local universe, right? So at cosmic noon and beyond that, typical ISM conditions of galaxies are different. So we have higher star formation rates. We have an increase in the star formation rate, in the average star formation rate density in galaxies of 1 order of magnitude, right? That's different, right, out of the box from the local universe. Not only that, we have a higher gas content. No, the reservoirs of gas in these galaxies also increase from the local universe to cosmic noon around redshift 1 to 2. In this case, not by a factor of 10, but by a factor of, let's say, 3, 4, right? Not only that, we also know that the gas fractions in these galaxies increase from the local universe to cosmic noon, from fractions that are of around a few percent to 10%, more or less, up to fractions that go up to 90%, right? So this is also different. We know that the star formation rate efficiencies are also different, right? At a higher redshift, or in this case is the depletion time scales, I guess, the inverse of the star formation efficiency, that the depletion time scales also goes down. So galaxies deplete faster their gas. And if you realize that this change is around a factor of 3 more or less, you combine it with the factor of 4 that you get in the increase of the molecular gas, and then you get to the order of magnitude that you see in the star formation, right? And because of this, all this, galaxies are forming stars at higher rates, right? You need, if you believe in a but if you think that the way that galaxies have to proceed with their star formation is that they should be accreting gas at the same rates, you obviously infer that the accretion rate, gas accretion rate in galaxies should be also larger at higher rates. So these are many ways in which, you know, we shouldn't expect by default that the paradigm on the formation of quasars at high redshift is the same as low redshift, right? So in order to study this, we took a look at a very particular population of high redshift quasars that are in a very particular phase of their evolution. These are called hot dust obscure galaxies or quasars, which is a population of galaxies detected by the WISE space telescope, which were selected to be strong mid-infrared emitters, but undetected or very faint in the near-infrared. As you can see here, they are very weak or non-detected in W1 and W2 near-infrared, but very strongly at 12 micron and 24 micron. There are around 2,000 of such objects in the entire extragalactic sky, and the redshift distribution is basically they peak at around redshift 2, and they span in a long tail down to redshift 3 and up to one guy here that I will talk a little bit later, specifically at redshift 4.6. The luminosity distribution of hot dogs, we know from Herschel observation that they are very luminous. The volumetric luminosities are in most cases, in almost all cases, above 10 to the 13 solar luminosities. And we have the most extreme population that obviously because of selection effects is at the highest redshifts. Above redshift 3, most hot dogs have infrared luminosities above 10 to the 14 solar luminosities. What is the typical spectral energy distribution of these things? Well, we see here that they are clearly, well, most 99% of the luminosity comes in the infrared, and they can have a very hot dust component, and that's why the name comes from the hot component. The hot part of the name that comes from the fact that they are not like dogs, which peak the peak of the SED, just simply those obscure galaxies, and the peak in which the peak of the SED is at a longer wavelength. We have dust heated up to 500 K, right? And this SED can be reproduced with some form of type 2 quasar that you also need to extra extinguish with an AB of 6 in order to bend the SED enough such that you get this steep downturn in the near infrared, right? And the problem with these super powerful quasars in the infrared is that they dominate the luminosity of the entire system down to rest frame 1 micron. So it's very difficult to see the galaxy below. You only see it in the optical. So what is remarkable is that most of the sources, most of the hot dogs show a very similar SED, which is obviously dominated by the quasar, and which also can dominate the continuum emission even at wavelengths larger than 100 micron. So another way of studying the interstellar medium of these objects are far infrared fine structure lines. And here, ALMA has been doing monumental work in probing all these far infrared fine structure lines that can give us information about the most basic and fundamental properties of the gas, such, for example, here, an example is the density of the gas, but it can be also the temperature or the intensity of the radiation field that they are exposed to, right? And this is the amazing work of ALMA can be exemplifying the fact that around 2005 there were only a few handful of sources observed in just one far infrared fine structure line, but now in the 2025 we have more than 1,000, right? This is the distribution of line luminosities as a function of redshift that we have currently. Now this is a review that Roberto and I are preparing for this year. So we took advantage of ALMA and we obtained all this array of line luminosities for a particular source for W2246. This is the highest redshift hot dog and also the highest, the one with the largest volumetric luminosity is like 3.5 times 10 to the 14 solar luminosities. Is the most luminous obscure quasar. And in a work by Fernandez Aranda, a PhD student working with me in Crete, he took all this set of emission lines, which you can see that some of them they are not detected, but most of them yes. And he created a massive set of cloudy models with which he compared all these line ratios. And one of the most surprising or interesting results is that he needed to incorporate a strong X-ray component in order to be able to reproduce some of these ratios. which is a little bit in contrast with other quasar populations at these higher redshifts. Also, it was very surprising not detecting the oxygen 388, but actually, the Claudia predicts that the high densities and strong X-rays, the composition of the XDR is very different from a PDR, and you should expect actually very little 88 micron emission. In addition to far infrared fine structure lines, with ALMA, we can look at the environment of these high redshift dusty quasars. And in particular for 2246, when we look at the cube that we obtained with observations of the C+ line, we actually detect 3 companions. One here that is almost at the systemic velocity of the central quasar. Another here, also very, very close in velocity. And finally, one here that you cannot see here because we miss it because it was at the edge of a spectral window, but that we confirmed later with observations of the Lyman alpha line with ground-based spectroscopy. So we knew that hot dogs live in large environments, but this was evidence that was provided by stacking of fields. So we didn't know exactly. We didn't know how prevalent these overdensities were, but now with ALMA, we can do this on individual objects, and 2246 looks like it's one of these overdensities. The finding companion galaxies around quasars was not particularly, new at the time, because this guy here had already published this impressive piece of work of detecting more than 20 quasars at redshift, even larger redshift, larger than 6, in which you could find companion galaxies detected in a number of sources at relatively short distances and with low velocity offsets. This work over here from Tanteprot and Nguyen also detected companion galaxies, SMGs basically, in quasars at a slightly smaller redshift, around 4.8. What was new at the time, though, was that what we discovered later with some more observations of we were targeting the nitrogen 2 line, and because this is a very faint line, we had to integrate very deep. And with it came an imaging of the dust continuum around 212 micron. And from this very point-like source that we had detected in C+, what we found when we look at the continuum was that we detected a completely extended and resolved structure that was very bright in continuum emission. We detected tidal tails that were coming and joining from the companion galaxies down to the quasar, and bridges of dust joining all this system of galaxies, right? And the detection of all this extended structure was like supporting evidence, direct evidence, that the most luminous obscure quasars, dusty quasars at cosmic noon and beyond, may be fed not only by like pristine. Okay, maybe a few minutes more. So not only pristine material from the cosmic web, but also metal-enriched gas from tidal streamers accreted from infalling interacting galaxies, right? But the thing is that from dust we don't have any kinematic information. So we went ahead and we integrate more than 12 hours on source on C+ to see what we can get from the kinematics. And this is what we got, right? We got emission everywhere. but not only very compact emission, but diffuse emission that was encompassing all the system. You can, and because we now can look at the kinematics, we can see that the whole system seems to be a kinematic component on its own. It's not only one galaxy, but we believe it's a system of 3 galaxies that are interacting with each other while orbiting around the main quasar, because they have their own kinematic component, and we see individual sources in there. And the entire system seems to be like smoothly kind of rotating in this direction, right? But the most interesting result was when we look at the velocity dispersion of the C+ line. We see this amazing swirling structure that you cannot see it here, but this comes up to almost 1,000 kilometers per second, like going around, right? So this may be in agreement with like this hypothesized isotropic blowout predicted by some models, given the luminosity of the quasar, which can predict this high velocity dispersion. So coming back to a little bit to the question of what is the paradigm of quasar, right? Can be the paradigm of quasars at high redshift. Is it a single continuous event like the established paradigm of the triggering of Euler phenomenon at low Z? Okay, we can take a look at the evidence. I haven't presented all the evidence in this talk, but I can give you a summary. We have a variety of morphologies. We have performed a pilot C+ survey on 7 galaxies, 7 hot dogs, and we see all kinds of morphologies. We can see all kind of dynamical states. We see rotating disk, we see complex kinematics, we see slow rotation, almost no rotation. So we see all kinds of things. And I showed the existence of companion galaxies for 2246, but we know from other observations that companion galaxies are present in most of the sources. And in some others, there is no companion galaxies, right? So extremely luminous hot dogs don't seem to be systematically at the latest stage of a major merger interaction, right? Like it is the paradigm of the formation of quasars in the local universe. So I think this is indirect evidence for a scenario in which extremely luminous hot dog phases could be actually recurrent or episodic, right? Because despite of being likely chaotic, because you find hot dogs in many settings, in many environments, with many morphologies, with many dynamical states. It's not only a late major merger interaction. And if this is true, if these are recurrent and episodic, the point is that they cannot be very long-lived, these episodes, because there is only one salpeter time before these supermassive black holes reach the masses that we see of the most massive black holes in the local universe, right? So it's like only 4 megayears of duty cycle. So at an Eddington ratio of 1, this can be, maybe a few of these events of a few mega years old duty cycle. So if recurrent, these episodes must be short, a few mega years old, depending on the total number. So finally, if I will rush through this, but these are JWST observations of 2246 that I wanted to present because they are new and they were published very few weeks ago by Andre Weiner. I forgot to include his name here, Weiner et al. 2025. It's posted in ElectroPH. This is a spectrum of the nucleus of 2246. You can see the velocities here, right? And this is systemic. So at most, H alpha in in the host is nothing compared with the amount of H-alpha and oxygen-3 in the outflow. There's one outflow component here. It's very complicated profile for the line, and another outflow component here that extends down to, I don't know, 13,000 kilometers per second, right? So there is clearly outflowing gas, but this is only seen in the nucleus. There is no spatially resolved outflowing gas anywhere else. So this is all confined to the central kiloparsec. If you look outside, this is in orange is the spectrum that you saw before, and then in blue is the typical region outside of the quasar. And you can see that there is no blue shifted component in anywhere else, right? We have maps for oxygen 2, H-alpha, oxygen 3, H-beta, and all the relevant optical emission lines that we got with near spec. And if we show this on a typical photoionization BPT diagram, we can see that if we plug in as a ionizing source the quasar, we cannot reproduce the ratios. We cannot reproduce the ratios that we see in the spatially resolved emission. But we can do so if we go to find what are the predicted ratios by models that include turbulence, right? So we can see that the regions that we've seen or in this galaxy, the ratios of the lines can be predicted by these models, and they are also in agreement with the velocity dispersions that we see in the lines, right? So this is very interesting because I don't know. Yes, here you can see it better when you distinguish between the sources, for example, here, the sources that have lines with less than 250 kilometers per second from the regions that have larger velocity dispersion than 250 kilometers per second. You can see that they are basically located in different spatial locations, and all the high velocity dispersion regions are surrounding the quasar. However, this is the interesting part. There's the conclusions already, but the interesting part is that we have these gigantic outflows, all confined in the center of the central kiloparsec of this quasar, and then everything that surrounds it is very turbulent, and is the excitation from this gas. It cannot be reproduced by ionization from the quasar. So there is something that is confining all this ionization to the central kiloparsec. And well, I don't have time to go here, but if you do the numbers, the energetics of the quasar that you get from the outflow are sufficient to power all this turbulence. But the photons are not escaping, which is a little bit puzzling, right? What we think that is happening is that you have very narrow channels through which radiation can escape, and then they are closed because galaxies are piling up in the center of these beasts. So in this case, you get some radiation out, it cascades down into turbulence, and then dissipates in the surrounding regions. But by the time that you see this, the lid is closed again, right? So we think that's what is happening in 2246, but we would like to verify if this is a property, or it's a similar scenario for other places. And I don't know if I have time to go through all the conclusions. I think I can cut it here, and I can take questions.